We'll conclude our treatment of chemical kinetics by looking at a very interesting application of a kinetic process, one that you've probably heard of, called radiocarbon dating. So what we want to learn in this case is how we use first-order kinetics to tell time. I should note that this is a material that's going to be very relevant to your Lab 4 analysis, so this is stuff that you probably want to get a hold of. All right, radioactive processes. Remember that the nucleus of an atom is made up of both neutrons and protons, and that we define different isotopes of a particular element that have a different mass, that is, they have a different number of neutrons associated with them. All right, this is something we learned very early in Chem 1083, but we haven't talked very much about that. What I want to do now is examine the process of radioactive decay, which is a process by which one isotope may convert into another, particularly if that isotope is unstable. So even though we have lots of isotopes, some of them are stable, but some of them are very unstable. And the way they convert themselves into other isotopes, or other elements in fact, is by undergoing a radioactive decay. Now, I'm going to tell you about two forms of radioactive decay. There are many others, but the two most prevalent ones are alpha decay, and this is shown here with a uranium-238 isotope decaying into thorium-234 and helium, and the alpha particle is actually the helium. Okay, so when these things were first discovered, they didn't realize that the alpha particle coming off was, in fact, a helium nucleus. That was determined later on. The alpha particle designation and alpha decay has stuck for this particular process. A second process is beta decay, in which a beta particle is emitted, and it turns out the beta particle is identical to an electron. And in this case, iodine is converted to xenon via beta decay. So with these kinds of radioactive decays going on, it opens up the possibility that we can have a radiometric dating method. And why is this possible? Well, the radioactive decay is a first-order decay, so that's very similar to chemical reactions. In other words, the rate law looks just like the first-order rate law, the integrated rate law, as drawn over here. And the half-life, similarly, does not depend on how much stuff you start with. It only depends upon the rate constant. So in fact, we can either define the half-life or the rate constant. Either one is sufficient to understand the rate at which a decay process will occur. So here's the strategy we're going to use in these radiometric dating methods. Well, first of all, every isotope has a certain abundance in nature, and it's kept at that abundance because there's an environmental equilibrium. It may decay at some rate, but then it's replaced by some natural process that replaces it. We'll talk a little bit about what that process is in the case of carbon in just a little bit. All isotopes, at least that we encounter, typically have some kind of mechanism where they're in an equilibrium in the environment. All right, a process could come along, though, that freezes their interaction with the environment. Now, in the case we're going to be talking about, that thing that interrupts the interaction with the environment is death. But in some instances, it may just be that a piece of matter, an isotope, becomes separated off. It becomes isolated from the rest of the environment, and so it can no longer exchange and no longer maintain that equilibrium. That then will undergo subsequent decay because these radioisotopes don't stay put for long. They will decay into another isotope or another element, and as it decays, that tells us something about how much time has passed since that interruption occurred. We then analyze that sample to find out what its current abundance is, so we can then compare it to see how many half-lives have passed since the interruption occurred. All right, and then this gives us, in a sense, the age of a sample. So let's suppose that you had a relative that collected stuff over time, but they had a finite size house, so they could only collect stuff up to a certain number. Like say they could collect 50 cars, and they didn't have room in their garage for more than 50 cars. They die. Okay, which interrupts their collection process. And now as time goes by, the family sells off the cars at some rate. All right, well, what one would find is that the number of cars is decaying away. And one could determine how much time has passed. If you know the rate at which the family is selling the cars, you would know how much, if you knew that rate, you would know how much time had passed since the older relative died. So this is a similar principle to what's going on here in radioactive decay. So how does carbon-14 dating work? Well, the equilibrium that's set up requires carbon-14 to be produced, which happens when nitrogen in the atmosphere is bombarded with neutrons from outer space. This creates carbon-14 and a hydrogen atom. It then decays by this process. So interestingly, carbon-14 is created from nitrogen-14 and it decays into nitrogen-14 via a beta decay process. So what that does is set up a sort of a cycle of carbon in the environment so that the percentage of carbon in the environment that's carbon-14 stays relatively constant over time. It keeps getting replenished. Now, there can be various kinds of disruptions to this. For example, volcanoes often cause disruptions. Meteors cause disruptions. There are man-made causes might disrupt a cycle for something. But in general, in the environment, we find that the amount of carbon-14 is relatively predictable. And it has been projected back over time to take account of these various disruptions so that we have a calibration curve that we can use to determine, based on the current abundance of carbon-14, we can determine sort of where it fit in the span of time in terms of when it was produced. So how would we analyze an organic sample? Now, this carbon-14 is going to decay at a certain rate, and we'll talk about what its rate constant is in a moment. But that rate, it looks very much like a first-order rate equation for chemistry. So the rate, the number of changes in the number of nuclei and that abundance of that isotope over time is going to be proportional to the number of atoms with that particular isotope. So, in other words, the rate is proportional to the amount of carbon-14 present in the sample. Now, interestingly, this provides us with a way to measure that amount. So if we can record the rate, and we usually do this with a Geiger counter, that actually can tell us something about what is the percentage of that particular isotope in the sample. So, for example, a live organic sample, the carbon-14 in a live sample would give a rate of 15.3 counts per gram per minute. All right, which is very nice. It gives us a very precise measure of how much carbon-14 we should expect to see if we're looking at an organism that's alive. So now here's a scenario that you might consider. Let's suppose we find a human skull fragment in an archaeological dig, and that skull fragment has a mass of 13.7 grams. Okay, so we have a very precise mass for that. And we then put a Geiger counter to it, and we find that we count 812 counts, decays of carbon-14, over a 5-minute period. Well, the first thing we would do is divide that 814 by 5 to find out that we get 162.4 counts every minute from that particular skull fragment. Now, we want to compare that against a live sample, but the live sample is a per gram unit, okay? So now we would want to divide by the number of grams, and we find that the count in this case is 11.85 counts per gram per minute. That's the actual carbon-14 decay count from this human skull fragment. So what we want to do is compare that to the live fragment and find out what percentage does that represent. Well, it represents 77.5% of the expected number. So now we can use that along with a first-order rate law to begin to determine when did this skull fragment have the 15.3 counts per gram per minute rate. So that tells us something about when did this person live. So once again, from the carbon-14 analysis, we found that the fraction of the current skull fragment has a 0.775 of the carbon-14 relative to the amount we would have expected. And we're going to set that equal to the first-order rate law for radioactive decay. So we have an equation that looks like this: 0.775 times the initial amount of radioactive carbon is equal to the initial amount of radioactive carbon times e to the minus kt. So we can directly set 0.775 equal to e to the minus kt. But what is k? That's one of the things we need to know. Well, it turns out that through extensive studies, we've found that the half-life of carbon-14 is about 5,730 years. So now we can simply use the fact that first-order rate processes K is equal to 0.693 log of 2 divided by this half-life, 5730 years. So when we do that calculation, we find that K for radioactive decay of carbon-14 is 1.21 times 10 to the minus 4 per year. So now I want to take the logarithm of both sides of this equation for n of t, and I'll find that log of 0.775 is equal to which equals minus 0.255, and now I've got to set that equal to log of e to the minus kt. And a log of e is just undoing the operation, so I'm going to get minus kt from that. And I know what k is. It's 1.21 times 10 to the minus 4. So I've got negative 0.255. The result of taking log of 0.775 is equal to negative 1.21 times 10 to the minus 4 times the time. So now if I need the time, I simply rearrange that equation. I find that the time that's passed is 2,110 years. So this human skull fragment belonged to someone who lived right about the time of the Roman Empire. Okay, so it's quite old. It's not impossibly old, but we can get a fairly good reading of its age simply from doing this carbon-14 analysis.